When we think about how we experience the physical world, we tend to heavily privilege our eyes.
Oh, absolutely. We're very visual creatures.
Right. I mean, you see a tree, you see a car, you see the screen in front of you, and it all feels incredibly concrete. Like if you want to know if something is real, you just shine a light on it.
Exactly. It's very binary, it's visible, and therefore it's comforting.
But I want you, the listener, to stop for a second and just listen.
Yeah, it is. It's a completely different way to map reality, isn't it? Because when you remove the visual aspect, you realize you're basically sitting in the middle of this constantly churning ocean of invisible pressure.
That is the perfect way to describe it. Because right now, wherever you are listening to this deep dive, there's a chaotic, completely invisible physical storm happening all around you.
Yeah, a storm of energy.
Right, you hear my voice, or maybe you hear, birds chirping outside, or waves crashing, a mobile phone ringing somewhere. All these everyday sensory experiences are just hitting you. But you can't see the physical mechanism connecting the event to your body.
No, it's an entirely invisible architecture.
And so our mission for this deep dive is to map that architecture. We've gathered a stack of comprehensive educational sources, specifically Chapter 10 on the science of sound, and we are going to explore the complete science of sound waves.
We're going to break down their characteristics, the pure mathematics behind them, and obviously their real-world applications.
Yeah, so if you've ever wondered what sound actually is on a physical molecular level, this is exactly where you need to be.
And to truly understand this invisible architecture, I mean, we really have to start by establishing a foundational rule of physics.
Okay, lay it on us.
So, sound is a form of energy.
Yeah.
And a fundamental law of the universe dictates that energy can neither be created from nothing, nor can it be destroyed into nothing.
Right, the law of conservation of energy, it just changes forms.
Exactly. It can only change from one form to another. So the initial question we have to ask is, well, what energy is being converted to create the sound of, say, a thunderclap or a plucked guitar string or even just the human voice?
And then, once that sound is born, right, once that energy is converted, how does it physically travel across an empty room, somehow navigate around your furniture, and just end up inside your head?
It's quite the journey.
It really is.
Yeah.
And we are going to take you on this continuous logical journey. We're starting at the very beginning with the birth of a vibration, moving through the mechanics of how it travels across space, and finally exploring how human biology actually intercepts that movement.
So let's start with how sound is born.
Yeah, let's do it. Our sources point back to some basic musical instruments to demonstrate this, which I think is helpful. Think about a bansuri, which is a traditional hollow bamboo flute.
Right, or a metallic instrument, call it datal, which is essentially a pair of hand cymbals.
Yeah, and the material really matters here. The text points out that the metallic tal possesses this property called sonority.
Yes, sonority. It's a critical material characteristic. It refers specifically to the ability of certain metals to produce a sustained, deep, ringing sound when they're struck.
As opposed to, like, hitting a piece of wood.
Exactly. If you strike a block of wood, you just get a dull thud. The energy dissipates super quickly into the internal structure of the wood itself.
Right.
But when you strike the sonorous metal of a tal, the actual atomic lattice of the metal allows the kinetic energy of the strike to reverberate. So the metal itself rings out clearly and sustains that energy over time.
Okay, before we get into the exact mechanics of that ringing metal, the research poses two really brilliant thought experiments that I just want to plant in your mind right now.
Oh, these are great, yeah.
So first, I want you to imagine two astronauts doing a spacewalk outside the International Space Station. They're repairing some big metal truss. Can they talk to each other directly or hear the loud clanking of their metal tools against the station the same way they would down here on Earth?
That scenario immediately challenges our sort of earthbound assumptions about how energy transfers. Because down here, we take the space between us for granted. Up there, the space is completely different.
Right. And the second thought experiment is more of a biological one. How do bats manage to navigate and locate tiny, fast-moving prey, like a moth, in total pitch-black darkness?
Which is just incredible to think about.
It is. And we are going to answer both of those mysteries as we build our understanding of the physics. But to get to those answers, we need to look at a classic hands-on experiment.
The rubber band experiment.
Yes, the rubber band. So picture taking a hollow cardboard box with one open side. You take a thick rubber band and stretch it right across that open gap. Then you hold the box steady, you pull the rubber band back with your finger, and you let it go.
So the initial observation here is purely sensory. You hear a sound, but simultaneously you get a vital visual confirmation.
Which is that the rubber band is a total blur. It's rapidly moving back and forth.
Exactly. And then you wait a few seconds, the rubber band gradually slows down as it loses its energy, and eventually it just stops moving entirely.
And the exact fraction of a second the rubber band stops vibrating, the sound completely ceases. So we have this very, very clear cause and effect.
Right. And we can manipulate that cause to see how the effect changes too. Like if you stretch the rubber band tighter, increasing the tension, and pluck it again, the type of sound changes.
The pitch goes up, right?
It does. You altered the physical state of the object, which altered the physical nature of its movement, which in turn altered the sound you heard.
And if you take that same rubber band off the box and just stretch it between your fingers in the empty air and pluck it, you still hear a sound, but it's dramatically softer than when it was stretched across that hollow cardboard cavity.
Because it doesn't have the box to resonate with. So bringing all these observations together gives us the core definition that really anchors this entire discussion.
Which is?
Sound is fundamentally produced by vibrations.
Vibrations, okay.
Yes. And we should define vibration in strict physical terms for a second. A vibration is the periodic to and fro motion or oscillation of an object.
So just an object moving back and forth past a central resting point over and over again.
Precisely. When you pull a stretched string or strike a sonorous metal cymbal, you are introducing kinetic energy that forces that material into a periodic to and fro motion. That physical vibration is the source of the sound.
But, I mean, obviously not all instruments use strings or metal. Like we mentioned earlier, if you blow into a bansuri, a flute, there's no rubber band to pluck. There's just a hollow tube of bamboo and the air from your lungs.
Right, which is a great point. In the case of the bansuri, the vibrating object isn't the instrument itself, but rather the actual column of air trapped inside the hollow pipe.
Oh, the air itself vibrates.
Exactly. When you blow across the hole, you create this fluttering vortex that forces the entire column of air inside the flute to oscillate back and forth. The air is the source. So whether it's a solid string, a stretched membrane on a drum, or an invisible air column, the object that is physically oscillating is the origin point of the energy.
Okay, let's unpack this and map it to our own biology, because I think that's where it hits closest to home. I want you, the listener, to right now just place your fingers gently against the front of your throat and hum a low note, like,
You can physically feel a distinct mechanical buzzing right there in your neck.
Yeah, it's wild when you actually pay attention to it. So what exactly is buzzing?
What you're feeling is your larynx, which is commonly known as the voice box. And inside your larynx are your vocal cords.
Well, they aren't actually chords, right?
No, they aren't strings like on a guitar. They're actually two tightly stretched muscular flaps. When you're just sitting quietly and breathing, these flaps are relaxed and open. They create this wide V-shaped slit that lets air flow freely in and out of your windpipe.
But when I want to talk, those muscles must have to, like, tighten up and close that gap.
They do. They pull tightly together, leaving only a very narrow slit. Then, your lungs act as a bellows, forcing a pressurized stream of air up your windpipe.
And when that pressurized air hits those tightly closed flaps,
It forces its way through that narrow slit, causing those muscular flaps to vibrate wildly.
wow, so we basically just have these biological rubber bands inside our throats. But, the vibration coming directly off the vocal cords isn't language yet, right? It's just a raw, buzzing tone.
Right, the raw buzz is just the power source. The rest of your vocal anatomy acts as a biological synthesizer.
Like your mouth and tongue.
Yes, your tongue, your lips, your teeth, the specific shape of your oral cavity, and even your nasal passages. They all rapidly shift and move to manipulate, filter, and shape that raw, vibrating buzz into distinct vowels, sharp consonants, complex speech, or even a melody.
That is fascinating. And, humans aren't the only species using specialized biology to generate these vibrations. The sources mention grasshoppers and crickets.
Oh, yes. The Summer Night soundtrack.
Right. Consider their loud, rhythmic songs.
Mm-hmm.
They don't have vocal cords or lungs pumping air. They produce their massive volume by a process called stridulation.
Which is such a great word.
It really is. Basically, they rub certain body parts together, usually this rough, comb-like edge on their legs against a scraper on their wings, to physically grind out those rapid vibrations.
It all comes back to that central, inescapable principle. To make a sound, you absolutely must force something to physically vibrate.
Okay, but visualizing that vibration isn't always as easy as looking at a blurry rubber band, right? Sometimes it's totally invisible to the naked eye.
That's very true. And to illustrate that, let's consider a tool designed for absolute acoustic precision, which is the tuning fork.
Ah, the classic science class tuning fork. Let's describe it for anyone who hasn't seen one in a while. It basically consists of a metal bar, typically machined from steel or aluminum, and it's bent into a U shape.
Right. And at the bottom of the U, there is a single straight stem for you to hold. The two upward pointing sides are called the prongs or the tines.
And this tool is engineered to vibrate at one very specific, consistent rate when it's struck. So if you hold it by the stem and strike one of the prongs gently against a soft rubber pad.
And our sources explicitly emphasize using a rubber pad, by the way, because if you strike it on a hard table, you can permanently warp the metal and completely ruin its precision.
Good safety tip for the tuning fork.
Uh-huh.
Okay, so you strike it on a rubber pad, and you hear a clear, pure ringing tone when you bring it near your ear. But if you actually look at it, the solid metal prongs don't look like they are moving at all. They appear perfectly still.
Yeah, their to and fro motion is so incredibly rapid, and the physical distance they move is so microscopic that the human eye simply cannot process the blur. It just looks completely static.
So how do we prove it's actually vibrating if we can't see it?
We have to introduce a visual medium. If you take that ringing tuning fork and gently touch the very tip of one of the prongs to the perfectly still surface of a bowl of water.
Oh, the result is dramatic.
It really is. The water violently splashes and you see this distinct pattern of ripples, these circular waves radiating out across the surface.
Because the water translates the invisible kinetic energy into a visible format.
Exactly. Because the solid metal prong is actually vibrating back and forth thousands of times a second, it acts like a microscopic hammer, repeatedly smashing into the water. It displaces the liquid, transferring its energy and creating those expanding waves.
So it's undeniable visual proof that the solid steel is engaged in violent physical motion.
It's a really elegant experiment.
Now, before we move on to how those vibrations actually travel through the air, I found this incredible real-world application in our sources regarding the human voice, and I have to bring it up.
Is this about Kongthon?
Yes, it's about a place called Kongthon, which is a village near Shillong in the Indian state of Meghalaya. It is famously known as the Whistling Village.
It's a stunning example of pushing that biological synthesizer of the human larynx to its absolute limits.
It really is. So in Kongthon, people don't just use standard spoken words for names. Every single person has a tune name that can be sung or whistled.
Right, a specific melody.
Yeah, this tradition is called Jingruai Yalbe, and it starts right at birth when a mother composes a totally unique lullaby-like melody specifically for her child. And that tune becomes their lifelong identifier.
This just highlights the incredible versatility of human vocal vibrations. We don't just use our larynx to transmit dry data via spoken syllables. We can manipulate the pitch, the duration, and the rhythm of those vibrations to create a completely unique acoustic signature.
And apparently, these tune names carry exceptionally well across the dense, hilly terrain of the village, which makes it a highly practical form of long-distance communication. And it's all born entirely from manipulating air pressure.
It's brilliant.
Okay, so we've established the birth of sound. Something must vibrate, a rubber band, a vocal cord, a metal prong. But that brings us to a massive logistical problem.
The distance problem.
Right, once that tuning fork is vibrating, how does the sound actually cross the physical distance of the room to reach your eardrum? We need to talk about propagation.
Propagation. It's the scientific term for the spreading or traveling of energy from its source to an observer. And the foundational rule of sound propagation is that the energy absolutely requires a material to travel through.
A medium.
Yes. We are accustomed to sound traveling through the air, which is obviously a gas. But energy doesn't care about the state of matter. It just needs atoms to interact with, so it can propagate through solids and liquids just as well.
Let's look at how you can test this yourself. First, solid propagation. Imagine you and a friend are standing at opposite ends of a long, solid wooden table. Your friend takes their fingernail and very gently scratches the surface of the wood at their end.
If you're just standing there, separated by 10 feet of air, you probably won't hear a thing, right? The sound is too faint to agitate the air enough to reach you.
But if you bend down and press your ear flat against the wooden surface,
You will hear the scratching with incredible clarity.
because the kinetic energy of the scratch didn't travel through the air, it propagated directly through the tightly bound atomic structure of the solid wood, traveling the entire length of the table straight into your ear.
Exactly. And the same principle applies to liquids. If you take a large bucket of water and you submerge your hands holding two metal spoons.
Making sure not to let the spoons touch the plastic sides or bottom of the bucket.
Right, that's crucial. and then you tap the metal spoons together underwater. You can actually hear the sharp clinking sound perfectly well while standing outside the bucket.
So in that instance, the vibration of the spoons transferred kinetic energy into the liquid water. The water propagated that energy to the surface where it transferred into the air and then propagated to your ear.
Exactly. Which leads to a critical scientific definition. Any physical material, whether it's a solid like wood, a liquid like water, or a gas like air, through which sound propagates is called a medium.
Okay, so sound demands a medium. It literally needs a physical material to ride on.
Mm-hmm.
Which begs the question, what happens if there is no material? What happens if you take the medium away entirely, creating a vacuum where there are no solids, no liquids, and no gas molecules?
To answer that, our sources detail one of the most famous demonstrations in physics, the bell jar experiment.
I love this one.
It's great. It's designed to completely isolate the variables of sound propagation. So you start with a heavy glass bell jar, which is basically a large, thick, airtight glass dome.
Okay.
Inside this dome, you suspend an electric bell, very similar to an old-school mechanical fire alarm. The bell jar is then placed on a sealed base plate that's connected via a hose to a powerful vacuum pump.
So step one is establishing the baseline. You turn on the electricity to the bell. You can look through the glass and visibly see the little metal hammer violently striking the metal gong.
And you can hear the loud, obnoxious ringing sound cutting clearly through the glass and the air in the room.
Right, because the chain of propagation is fully intact. The kinetic energy is transferring from the bell into the air inside the jar, into the glass, into the room's air, and finally into your ear.
Exactly. Then you introduce the disruption. You turn on the vacuum pump.
Here we go.
The pump begins mechanically sucking the air molecules out of the sealed glass jar. As the air gets progressively thinner, meaning there are fewer and fewer gas molecules inside the dome, the sound of the bell noticeably drops in volume.
It becomes fainter and fainter.
Oh, yeah.
And this is the part that just completely messes with your brain. You are looking right at the bell. You can clearly see the metal hammer still striking the gong with the exact same mechanical violence.
The visual evidence of the energy hasn't changed at all. The bell is vibrating just as hard.
But the audio is disappearing.
Right. And eventually the pump achieves a near vacuum. Almost all the air particles have been evacuated. At this point, the sound drops to absolute silence.
Wow.
You see the hammer striking the bell, but you hear absolutely nothing. The chain is broken, the bell is vibrating, but there are no air molecules surrounding it to absorb and transfer that kinetic energy to the glass. The energy is basically just trapped.
And if you then open a release valve on the base plate, allowing the air from the room to violently rush back into the jar.
The loud ringing sound instantly materializes again. The medium is restored, and so is the propagation.
That dramatic demonstration perfectly resolves our first thought experiment regarding the astronauts.
Yes, it does. Outer space is, for all practical purposes, a vacuum. There's no atmosphere, no gas, no medium occupying the vast distances between objects. Therefore, sound simply cannot propagate.
So if an astronaut is fixing a truss and accidentally bangs their heavy metal wrench against the space station, the metal wrench and the station vibrate violently. But because they are surrounded by the vacuum of space, there are no particles to carry that vibration away.
Right. The astronaut floating 10 feet away won't hear a thing.
They are visually occupying the same space, but acoustically they are entirely isolated in separate universes.
Which is why, to communicate, they can't rely on sound waves. They must use specialized headsets inside their pressurized, air-filled helmets that convert their voices into radio waves.
And radio waves are a form of electromagnetic radiation, which operates under an entirely different set of physics and does not require a physical medium to travel.
Exactly. So sound absolutely requires a medium. We've proved that.
But I'm still trying to wrap my head around the physical mechanics of how it travels through that medium. Like, if the tuning fork vibrates, what are the air particles actually doing? Are they flying across the room like tiny bullets to hit my eardrum?
No, that's a very common misconception. If sound worked that way, every time someone shot it at you across a room, you'd feel a massive blast of wind hitting your face.
Right, which obviously doesn't happen.
The particles themselves do not travel from the source to the destination. To visualize what actually happens, the research uses an exceptional analogy involving a slinky. You know, the classic coiled metal spring toy.
Oh yeah, I can picture it. So you lay a long, slinky flat on a smooth floor. You have a friend hold one end perfectly still so it doesn't slide away. You hold the other end, stretching the slinky out just enough so there's some tension.
Okay, now, you give your end a sharp, sudden push directly towards your friend and immediately pull your hand back to its starting position.
And what happens next is mesmerizing. You'll observe a localized disturbance traveling down the length of the slinky. You'll see a small section where the metal coils bunch up tightly together.
Yes, and immediately behind that tightly bunched section, you will see a section where the coils are stretched abnormally far apart.
This paired pattern of bunched and stretched coils travels rapidly away from your hand down the entire length of the slinky until it hits your friend's hand.
But here is the secret to understanding sound.
Yeah.
You have to focus on a single piece of the medium rather than the whole traveling wave.
Okay, so imagine before you push the slinky, you take a bright red marker and paint one single metal coil right in the dead center of the toy. When you push and create that traveling disturbance, watch only the red coil.
What you will observe is that the red coil does not travel down the slinky to your friend's hand. As the disturbance reaches it, the red coil is violently shoved forward into the coil next to it.
And then as the stretched portion passes, the red coil gets pulled backward.
Exactly. Ultimately, the red coil just wiggles forward and backward, returning almost exactly to its original resting position.
It oscillates in place. It absorbs the energy, bumps into its neighbor to pass that energy along, and then snaps back. The disturbance, the energy, travels the entire distance, but the medium itself stays mostly put.
That's it, exactly. When your vocal cords vibrate, they smash into the air molecules immediately inside your throat. Those molecules bump into the next layer of air, which bumps into the next layer. The kinetic energy cascades outward in a domino effect of microscopic collisions.
To map this to the air in a room, our sources introduce a second mechanical analogy: a hollow tube with a movable piston.
Right, this is a great visualization.
So imagine a long, transparent glass tube filled with normal air. At one end is a tight-fitting piston that can push in and pull out. When the piston is at rest, the air molecules inside the tube are bouncing around randomly, but overall they are spaced out evenly.
We call this baseline state the average density, or normal atmospheric pressure. Now, you take that piston and shove it violently forward into the tube.
That physical intrusion forces the air molecules immediately in front of the piston to squish tightly together.
Yes. You've forcefully crammed the same amount of matter into a smaller volume. You've created a localized zone of high density and high pressure. And in acoustic physics, this high pressure zone is called a compression, denoted by a capital C.
Compression. Makes sense. Because those molecules are now uncomfortably close together, their natural repulsive forces cause them to spring outward. They slam into the layer of molecules immediately in front of them, squishing that new layer together, while the original layer bounces back toward the piston.
Right, and in this way, the compression, the C zone, travels down the tube away from the source. Now, immediately after pushing the piston forward, you yank it sharply backward.
This sudden withdrawal leaves behind an empty void. The air molecules rush to fill this extra space, spreading much further apart than their normal baseline.
So you've created a localized zone of low density and low pressure. This is called a rarefaction, denoted by a capital R.
Rarefaction. And just like the compression, this rarefaction zone propagates down the tube, following immediately on the heels of the compression.
So if you attach that piston to a high-speed motor, so it's vibrating rapidly back and forth, essentially simulating a tuning fork or a vocal cord, you generate a continuous alternating train of high-pressure and low-pressure zones.
Compression, rarefaction, compression, rarefaction.
Right.
CR.
Exactly. This traveling sequence of density changes is the sound wave.
I've always wondered about extreme examples of these pressure waves, and the research touches on something incredibly dramatic: the sonic boom.
Oh, yes!
Like, how does a jet aircraft create a sound that can literally shatter glass on the ground?
A sonic boom is a phenomenal demonstration of these compressions stacking up. When an aircraft is flying at normal speeds, the sound of its engines, the compressions it's creating, travel out ahead of the plane, clearing the way.
But as the plane accelerates to supersonic speeds, it is physically moving faster than the speed of sound. It is outrunning its own compressions.
Precisely. Because the compressions can't get out of the way, they begin to forcibly stack up on top of one another right at the nose of the aircraft.
Like pushing a wave of water in a pool.
Yeah, and they merge into a single, massive, incredibly dense shock wave of extreme pressure. This shock wave takes the shape of a massive cone trailing behind the jet.
And when the edge of that high-pressure cone eventually drags across the ground and hits your body and ears.
The sudden, violent change in atmospheric pressure is perceived as a deafening explosion, the sonic boom.
Wow. It is pure, raw mechanical energy violently displacing the medium. Now, because of how the particles behave during this displacement, physics categorizes sound into a very specific family of waves, right?
It does. Let's look back at the slinky. The energy traveled forward from your hand to your friend's hand. And how did the individual coils move?
They wiggled forward and backward along that exact same path.
Right, because the individual particles of the medium vibrate parallel to the direction of the wave's propagation, sound is officially classified as a longitudinal wave.
Longitudinal, meaning along the length of the travel. This makes sense. But wait, what is the alternative? How else could a wave travel?
Think about a stadium wave at a football game. The wave travels horizontally around the circular seating of the stadium. But what are the people actually doing?
They're standing straight up and sitting straight down. Their physical motion is up and down, but the energy travels left to right.
Yes. Or imagine holding a rope tied to a wall. If you whip your hand up and down, a wave travels horizontally toward the wall. But any specific piece of the rope is only moving vertically.
Okay, I see.
When the particles of the medium vibrate perpendicular to the direction the wave is propagating, it's called a transverse wave.
And the sources point out that earthquakes are actually terrifyingly perfect laboratories for this. When tectonic plates snap, they release unimaginable energy that travels through the Earth.
Right, and they produce both types.
Yeah, they produce longitudinal seismic waves, called P waves, which compress and rarefy the solid rock. And they produce transverse seismic waves, called S waves, which shear the rock side to side. And the longitudinal P waves travel much faster and hit the seismographs first.
And we absolutely must mention the most famous transverse wave in the universe, which is light. Light waves oscillate perpendicularly to their direction of travel. But what makes light truly exceptional and fundamentally different from sound is its relationship with the medium.
Because light doesn't need one, which is why we aren't completely blind. The light from the sun and distant stars traverses millions of miles of the hard vacuum of space to reach our retinas.
Exactly. Because sound inherently requires a physical material, a medium, to propagate its energy through physical particle collisions, we classify sound as a mechanical wave. It relies entirely on the mechanics of matter.
Sound is a longitudinal mechanical wave. Light is an electromagnetic wave.
You've got it.
And this mechanical transfer of kinetic energy is exactly what allows modern audio technology to function. Let's look at microphones and speakers for a minute. Because how do we capture an invisible pressure wave and turn it into a podcast?
It's all about capturing the mechanical force of those collisions. Imagine the inside of a microphone. Behind the metal grill, there is an incredibly thin, ultra-sensitive membrane called a diaphragm.
Usually made of lightweight plastic or aluminum, right?
Often, yes. When you speak into the microphone, you're launching that alternating train of compressions and rarefactions across the air.
And when a high-pressure compression hits the diaphragm, the tightly packed air molecules physically slam into it, pushing the membrane inward.
Right. And then a millisecond later, the low-pressure rarefaction arrives. Because the pressure on the outside is now lower than on the inside, the membrane snaps back outward.
So the diaphragm of the microphone is forced to physically vibrate back and forth in perfect synchronization with the air pressure changes caused by your vocal cords.
Exactly. The microphone then utilizes electromagnetic principles, often a tiny coil of wire moving through a magnetic field attached to that diaphragm, to translate that physical mechanical movement into a fluctuating electrical current.
So the mechanics become electricity. We record that electricity, send it over the internet, and then your headphones or speakers have to do the exact reverse.
A speaker takes that fluctuating electrical signal and runs it through an electromagnet attached to a paper or synthetic cone.
And as the electricity pulses,
The magnet rapidly pushes and pulls the cone. The cone forcefully shoves the air molecules in front of it, mechanically recreating the exact sequence of compressions and rarefactions.
so if the engineering is precise, the physical pressure wave hitting your ear right now is a near-perfect replica of the pressure wave that left my mouth.
It is a miraculous translation engine. Mechanical kinetic energy to electrical data, back to mechanical kinetic energy.
It really is. But here is where I have to admit some serious confusion, and I need you to clarify something that contradicts everything we just talked about.
Uh-oh. What is it?
We have thoroughly established that sound is a longitudinal wave. The particles move horizontally back and forth parallel to the wave. Why then does every single science textbook, Every audio editing software and every diagram in our source material draw a sound wave as a wavy line going up and down. That looks exactly like the transverse rope wave you just described.
Ah, this is such a good question. This is perhaps the single most common stumbling block when people first study acoustics. It is incredibly counterintuitive.
Right, it doesn't match the physics we just talked about.
The disconnect happens because you are looking at the wavy line and interpreting it as a physical picture of the wave in space. It is not.
Okay, then what is it?
That wavy line going up and down is a mathematical graph plotting two very specific variables, density versus distance.
Okay, let's break that graph down slowly.
Picture a standard graph. You have a horizontal x-axis and a vertical y-axis. The horizontal x-axis represents the physical distance stretching away from the source of the sound, say, moving across the room away from a speaker.
Got it.
The vertical y-axis represents the density or the pressure of the air molecules at any given point.
And usually there's a straight dashed line running horizontally right through the middle of the graph.
That dashed center line is the baseline. It represents the average density of the quiet air before any sound is introduced. It's just the normal atmospheric pressure. Now remember the piston.
Yeah, when it pushes forward, it creates a compression, a localized zone where particles are squished together, resulting in high density and high pressure.
So because the pressure is higher than normal, the line on the graph has to go up.
Oh, I see.
Exactly. On our graph, a compression is plotted as the curve rising up above the average density baseline. The line going up does not mean the air molecules are physically flying upward toward the ceiling. It simply signifies that the density of the air is increasing at that specific distance from the speaker.
And the absolute highest tip of that curve, representing the moment of maximum crushing density, is called the crest of the wave.
Yes, the crest.
That makes so much more sense. And when the piston pulls back, creating the rarefaction, the air gets thinner. The density drops below normal.
And therefore, on the graph, the curve dips down below the baseline. The absolute lowest point of that valley, representing the moment of maximum emptiness or lowest density, is called the trough of the wave.
So the wavy up and down line is nothing more than a mathematical map of pressure. High pressure, low pressure, high pressure, low pressure. Crest, trough, crest, trough. It is charting density, not physical direction.
Exactly. And our sources add a fantastic caveat about that baseline state of the air that we really shouldn't overlook.
What's that?
When we talk about the air being at rest, at average density, we don't mean the microscopic molecules are just frozen in place.
Right, they possess thermal energy.
Exactly. Simply because the room isn't at absolute zero, those air molecules are constantly vibrating, zipping around, and crashing into each other in total random chaos.
Like a microscopic mosh pit that never stops.
Yes. When a sound wave passes through the room, it does not initiate movement from a dead stop. It simply imposes a highly organized directional cascade of collisions on top of that existing chaotic thermal wiggling.
The sound wave is a temporary order forced upon the chaos.
And once the sound wave passes, the molecules instantly revert back to their random thermal dancing.
That is a beautiful way to visualize the micro-reality of a room. All right, now that we understand how to read the graph, crests and troughs, we can move into the pure mathematics of sound.
Yes, we need to define the specific characteristic that allow us to measure these waves. Let's start by defining a single event.
Okay, what is the single event?
In wave mechanics, the fundamental unit of measurement is one complete oscillation. Imagine you're standing at a fixed point in the room with a pressure meter. As the sound wave washes over you, the air pressure will rise to a maximum high, the crest drop all the way down to a minimum low, the trough, and then rise back up to the maximum high again.
So that entire sequence, from maximum to minimum and back to maximum, constitutes one complete oscillation.
Precisely. Now that we have our unit, how do we measure its behavior over time? The research introduces two deeply connected mathematical concepts, frequency and time period.
Let's tackle frequency first.
Frequency answers a very simple question: how often? If you remain at that fixed point in the room, frequency measures how many of those complete oscillations pass you by in exactly 1 second.
So it's a measure of rate.
Yes. In physics, frequency is often represented by the Greek letter nu, which looks a bit like a lowercase v. And the universally accepted standard unit of measurement for frequency is the hertz, abbreviated hertz.
Okay, so if a wave completes one full oscillation per second, it has a frequency of 1 hertz.
Correct.
So if a tuning fork is vibrating incredibly fast and it sends 440 complete crest to crest waves past my ear in a single second, that sound has a frequency of 440 hertz.
Precisely. Now, the flip side of that perspective is the time period. represented in equations by a capital T.
And how is that different?
Instead of asking how many in a second, the time period asks how long for just one. It is the exact duration of time, measured in fractions of a second, required for one single complete oscillation to pass a fixed point.
So they are essentially looking at the exact same physical event from two different angles. Frequency is the count per second. Time period is the seconds per count.
Because of this relationship, the formulas show they are mathematical inverses of each other.
The equation is beautifully simple, right? Frequency equals 1 divided by the time period.
Yes, if you know how long one wave takes, you automatically know how many happen in a second, and vice versa. As frequency increases, the time period naturally must decrease.
Okay, we've measured time. Now let's measure the physical force. Let's look at the vertical y-axis of our graph, the density map. This introduces the concept of amplitude.
Amplitude is a measure of magnitude. It is defined as the maximum physical displacement of the particles from their mean resting position.
So on our graph, amplitude is represented by the height of the crest above the dashed baseline, or the depth of the trough below it.
Yes. A larger amplitude means the air molecules are being squished together much tighter during a compression and pulled much further apart during a rarefaction.
And fundamentally, that larger displacement requires more physical force to achieve. So amplitude is a direct proxy for energy.
Exactly. A wave with a larger amplitude is carrying a significantly greater amount of kinetic energy. To conceptualize this, the sources suggest an experiment using a metal plate with small grains of sand or sugar sprinkled on it.
Oh, I've seen videos of this.
It's a great visual. If you tap the edge of the plate gently with a stick, you impart a small amount of kinetic energy. The metal plate vibrates with a very small amplitude. The resulting sound is quiet, and the grains on the surface merely dance a fraction of a millimeter into the air.
But if you take that stick and violently smash it against the plate,
You transfer a massive load of kinetic energy. The metal plate's displacement, its amplitude, is huge. The sound is deafening, and the grains of sand are violently launched inches into the air.
the physical amplitude of the source dictates the energy of the wave.
Yes. And this concept of energy flow leads to a very rigid, objective physics term: intensity. People often confuse intensity with loudness, but in physics, intensity is a cold, hard number.
How is it defined?
Intensity is strictly defined as the amount of sound energy passing through a unit area, say 1 square meter, that is held perpendicular to the direction of the wave in 1 second.
So it's an absolute measurable quantity of power washing over a specific area measured in watts per square meter.
Yeah.
It does not care if anyone is actually there to hear it.
Exactly.
Okay, we have the time, which is frequency, and we have the energy, which is amplitude. Now we need the physical size. This brings us to wavelength.
Wavelength is wonderfully tangible. It's represented by the Greek letter lambda, which looks like an upside-down wave. Wavelength is literally the physical distance in space between two consecutive points of maximum density, the distance between one crest and the very next crest.
Or conversely, the distance between two consecutive troughs.
Right.
So if you could freeze time and hold a tape measure in the air, you could literally measure the physical length of one complete wave in inches or meters.
You could. And once we have the physical length of the wave and we know how long it takes to pass by, we can calculate the final characteristic, speed.
The foundational equation for speed in physics is distance divided by time, right?
Yes. So if we apply this to a sound wave, the distance of one complete cycle is the wavelength. The time it takes for that one cycle to occur is the time period.
Therefore, the speed of the wave equals the wavelength divided by the time period.
And because we established earlier that 1 divided by the time period is the exact same thing as frequency, we arrive at the classic wave equation used by physicists everywhere.
Speed equals wavelength multiplied by frequency.
It's a very elegant relationship. However, there is a massive caveat regarding the speed of sound that we need to address.
What is it?
The speed is not determined by the frequency, and it is not determined by the amplitude. A loud, low-pitched bass note does not travel any faster than a quiet, high-pitched whistle.
Wait, really? So what determines the speed?
The speed of a sound wave is determined almost entirely by the physical properties of the medium it is traveling through.
And this brings us right back to solids, liquids, and gases.
Wow.
The density and the elasticity of the material dictate the speed of the energy transfer.
Yes. Sound travels at dramatically different velocities depending on the state of matter. It travels the absolute fastest through solid materials.
Because in a solid like steel or aluminum, the atoms are packed incredibly tightly together in a rigid, highly structured atomic lattice. They are strongly bound to one another.
Exactly. So when one atom vibrates, it has virtually no distance to travel before it smashes into its neighbor, instantly passing the energy down the line.
Ah, you see?
Because of this tightly bound structure, sound travels through solid steel 15 to 20 times faster than it does through the air you're breathing right now.
That's crazy fast.
It is. It travels slightly slower through liquids, like water, because the molecules are still close together but have more freedom to move. It travels roughly 4 to 5 times faster in water than in air.
And it travels the slowest in gases, like our atmosphere, because the gas molecules are spread relatively far apart. A vibrating air molecule has to actually travel across empty microscopic space before it happens to collide with another molecule to pass the energy along.
This physical reality is why, in historical accounts and old Western movies, you see someone pressing their ear directly against the solid steel railroad tracks to listen for a distant train.
Oh, right. Because the low-frequency rumble of the train's wheels travels through the solid steel track vastly faster and with significantly less energy loss than the airborne sound.
Exactly. They can hear the train through the steel miles before they can hear it through the air.
So everything we have discussed up to this point has been pure, objective physics. Frequencies in hertz, wavelengths in meters, amplitude, intensity. These are cold, calculable facts of the universe.
They are.
But human beings are not scientific instruments. We don't read the world in data tables, we experience it subjectively. And this brings us to the bridge between physics and biology. Human perception.
This is where it gets truly fascinating. Because while a microphone mathematically measures frequency and intensity, the human brain subjectively translates those physical properties into entirely new qualitative experiences: pitch and loudness.
Let's start with pitch. Pitch is simply the subjective psychological way our brains interpret the physical reality of frequency.
Right. When a sound wave has a very high frequency, meaning the tuning fork is vibrating incredibly fast, and hundreds of tightly packed compressions are slamming against your eardrum every second, your brain decodes that rapid-fire data stream and presents it to your consciousness as a high pitch.
We often describe these sounds as shrill or sharp, like the piercing blast of a referee's whistle or the wail of an ambulance siren.
Conversely, if the physical wave has a low frequency, meaning the object is vibrating sluggishly, and the compressions are hitting your eardrum much slower with significant gaps of time between them, your brain interprets that slower data rate as a low pitch.
A deep, heavy sound, like the ominous rumble of thunder or the drone of an airliner at high altitude.
This relationship explains a fascinating biological mystery that our sources touch upon. Why do human voices change, and why do we all sound different?
Right. We established earlier that we all use the exact same basic mechanism, the muscular vocal flax in the larynx, to generate the vibration. So why do I have a distinct voice, and you have a distinct voice?
It comes down to the microscopic differences in the physical dimensions of those vocal cords, combined with the resonant cavities of your chest and skull.
Like the size of the instrument.
Yeah, exactly.
Yeah.
The clearest example is puberty. As boys go through adolescence, hormonal changes trigger rapid anatomical growth. The cartilage of their larynx grows, often visibly as an Adam's apple, and more importantly, their vocal cords literally grow longer and substantially thicker.
Going back to our rubber band analogy, a thick, heavy rubber band is much harder to vibrate quickly than a thin, snappy one.
Exactly. Because the biological mass of the thickened vocal cords increases, they vibrate less frequently when air pushes past them. This physically lowers the frequency of the sound waves they produce.
And your brain perceives that lower physical frequency as a dramatically deeper, lower-pitched voice.
Yes.
Okay, so pitch is our subjective translation of frequency. What about the power of the wave? That brings us to loudness. Loudness is how the human brain subjectively perceives the amplitude or the intensity of a sound wave.
When a wave has a massive amplitude, the compressions are incredibly dense. They hit your eardrum with tremendous physical force, violently pushing it far inward. Your brain interprets this violent, high-energy displacement as a loud sound.
But the sources draw a very sharp line here that we really need to emphasize. Intensity is the physical, objective energy passing through the air. Loudness is an entirely subjective biological response.
It is a critical distinction. Intensity exists independent of the observer. Loudness depends entirely on the sensitivity of the listener's ear and brain.
Right, like a jet engine produces a sound wave of massive physical intensity. But if a person standing nearby has severe hearing damage, their biological equipment fails to capture that energy, and their brain does not perceive it as loud.
Furthermore, the subjective loudness naturally decreases as you move further away from the source.
Why is that?
Well, the initial kinetic energy of the vibration spreads out over an increasingly massive area of air as the spherical wave expands outward. By the time it reaches you a mile away, the amplitude has decayed to a fraction of its original strength.
Oh, that makes sense. To map this intensity in a way that aligns with human perception, scientists use a logarithmic unit of measurement called the decibel.
The decibel scale is brilliant because it compresses the vast, incomprehensible range of acoustic energies into manageable numbers. The absolute threshold of human hearing, the faintest sound a healthy ear can detect, is defined as 0 decibels.
And the incredibly gentle rustling of leaves in a breeze registers at roughly 10 decibels. A normal, relaxed conversation between two people in a quiet room is about 60 decibels.
But when you get into heavy industrial noise or loud events like setting off firecrackers, you easily push past 100 decibels.
And this is where the public often dangerously misunderstands the scale. Because it is logarithmic, not linear, a small numerical increase on the decibel scale represents a terrifying, explosive multiplication of actual physical energy.
Going from 60 to 70 decibels isn't just a small step up. The sound at 70 dB is 10 times more intense than at 60 dB.
Which perfectly transitions into a major public health concern highlighted in the research: noise pollution. In physics, noise isn't a specific frequency. It is defined functionally as any unwanted, unpleasant, or physically harmful sound.
And the biological equipment in our ears is incredibly delicate. Exposure to extreme decibel levels or even moderate levels for extended, relentless durations, like working an 8-hour shift in a loud manufacturing plant or blasting music through earbuds all day, can have devastating health impacts.
Because the constant stress of that acoustic energy disrupts sleep architecture, elevates cortisol and blood pressure, and physically degrades the microscopic mechanics of the inner ear.
That physical degradation leads to irreversible hearing loss. The delicate sensory cells simply die from overwork. Medical professionals test for this degradation using specialized charts called audiograms, which map exactly which frequencies a person is losing the ability to hear.
Fortunately, biomechanical engineering offers a workaround for this biological failure: the hearing aid. And what is beautiful is that a hearing aid is simply a miniaturized, wearable version of the audio technology we broke down earlier. It is a closed loop of energy conversion.
It has a microscopic microphone on the outside to catch the incoming compressions and convert them into electricity. It has a tiny computer amplifier to artificially boost the voltage of that electrical signal.
And it has a microscopic speaker sitting right inside the ear canal to convert that massive electrical boost back into highly amplified mechanical air pressure waves, forcefully driving the damaged eardrum to vibrate.
Which brings us to the final and perhaps most miraculous piece of this biological puzzle.
How does the human body actually catch this mechanical waves and send it into consciousness?
The anatomy of the ear is basically a microscopic Rube Goldberg machine. Let's trace the journey of a single compression.
Okay. The wave of high pressure enters the outer flap of your ear, which acts as an acoustic funnel, and travels down the dark tunnel of your ear canal.
At the very end of this tunnel, it smashes into the tympanic membrane, more commonly known as the eardrum.
And the eardrum is an incredibly thin, tautly stretched cone of skin. It acts exactly like the diaphragm of the microphone we discussed.
Yes, when the high-pressure compression hits it, it bows inward. When the low-pressure rarefaction arrives, it bows outward. It is forced to mechanically mirror the exact frequency and amplitude of the invisible wave.
Attached directly to the back of this vibrating eardrum are the ossicles. Three bizarrely shaped tiny bones located in the middle ear. They're called the malleus, ingocatus, and stapes, or the hammer, amble, and stirrup.
They are the smallest bones in the human body, and these three bones act as a complex mechanical lever system.
They take the relatively large, weak vibrations of the eardrum and concentrate that kinetic energy down into a much smaller, incredibly forceful vibration. They act as an organic, mechanical amplifier.
The final bone, the tiny stirrup, plunges like a piston into a membrane called the oval window, which guards the entrance to the inner ear.
The inner ear houses the cochlea. This is the main event. It looks like a tiny, coiled snail shell embedded deep in your skull, and it is completely filled with liquid.
When the stirrup punches the oval window, it sends shock waves rippling through the fluid inside the cochlea. Lining the inside of this fluid-filled snail shell is a highly complex structure called the basilar membrane, which is covered in tens of thousands of microscopic hair-like sensory cells.
As the fluid ripples and sloshes around, it physically bends these tiny hairs back and forth.
And here's the exact moment of magic. When those specific hair cells bend under the mechanical force of the fluid wave, they trigger a chemical reaction that generates an electrical voltage.
The mechanical kinetic energy of the universe is finally, definitively converted into biological electricity.
Those electrical nerve impulses instantly shoot up the auditory nerve, traveling directly into the auditory cortex of your brain, where the raw data is instantly decoded, analyzed, and presented to your conscious mind as the sound of my voice.
And this entire wildly complex chain of events, from my vocal cords, across the room, down your ear canal, through the bones, into the fluid, into electricity, into consciousness, happens in fractions of a single second.
It is the ultimate translation engine, physics becoming biology, biology becoming subjective reality.
We have covered an immense expanse of scientific territory today. Let's pull the lens back and synthesize the entire journey to make sure these concepts are really locked in.
So if we summarize the absolute foundational truths of this field, first, sound is an energy transfer initiated strictly by vibrating objects, objects moving in a periodic to and fro motion.
Second, it is a longitudinal mechanical wave. It mandates a physical medium, whether that is a solid table, liquid water, or gaseous air. Without matter, as we saw in the vacuum of the bell jar, the energy cannot propagate.
Third, the wave travels, but the medium remains. The individual particles do not fly across the room. They merely vibrate back and forth in place, bumping into their neighbors to pass the cascading disturbance of high-pressure compressions and low-pressure rare arefactions forward.
Mathematically, we measure the physical distance between those compressions as the wavelength. We measure how many pass by in a second as the frequency, which our brains perceive as pitch. And we measure the physical displacement, the power, as amplitude and intensity, which we subjectively experience as loudness.
Finally, the speed of this energy transfer is dictated primarily by the state of the medium, traveling at its absolute fastest through the tightly bound atomic lattices of solids and slowest through the spread-out molecules of gases.
Before we wrap up, the research highlights two phenomenal behavioral quirks of sound that perfectly tie off our earlier mysteries. First, sound waves can bounce.
Yes, reflectant.
When a propagating wave hits a large, hard, solid obstacle, like a cliff face or the walls of an empty cathedral, the kinetic energy doesn't just absorb, it reflects back into the medium. This reflection of sound energy is what creates echoes and complex reverberations.
The second quirk involves the limits of our biology. The human ear can only detect frequencies between 20 Hz and 20,000 Hz.
Any mechanical wave vibrating slower than 20 times a second is called infrasonic. We can't hear it, but massive animals like elephants and whales use these deep, low-energy waves to communicate over vast distances.
Conversely, any wave vibrating faster than 20,000 times a second is called ultrasonic. It is simply too fast for our tiny ear bones to process, which finally answers our second thought experiment from the very beginning.
How do bats hunt a tiny moth in total pitch-black darkness?
They utilize a combination of ultrasonics and reflection. Bats possess the biological capability to scream at incredibly high ultrasonic frequencies, sometimes up to 100,000 hertz. They emit rapid pulses of this high-frequency sound into the dark air ahead of them.
When those invisible high-speed compressions hit the tiny body of a flying moth, they reflect off the insect and bounce back through the air toward the bat.
And the bat's massive, highly sensitive ears catch that faint returning echo. By instinctively calculating the minuscule time difference between when they emitted the pulse and when the echo returned, their brains can instantly calculate the exact distance, direction, and speed of the moth.
They are literally mapping the three-dimensional space using pure acoustic reflection. It is biological sonar, operating perfectly within the mechanical rules we just explored.
It is the perfect synthesis of physics, biology, and environmental adaptation.
It truly is. Now, as we close out this deep dive into the invisible architecture of our world, we always like to leave you with a provocative thought to mull over.
Consider the final step of the acoustic journey we traced, the microscopic hairs inside the cochlea physically bending to translate mechanical air pressure into purely electrical signals for your brain. It raises a deeply philosophical question about the nature of reality.
What's the question?
If the physical world outside your skull is, objectively, nothing more than silent air molecules violently bumping into each other in a cold mechanical sequence of compressions and rarefactions, is the beautiful, emotionally moving sound of a cello sonata actually out there in the room? Or is the concept of sound an entirely electrical illusion, a breathtaking hallucination created exclusively inside the dark, silent theater of your own brain?
That is a staggering thought to leave you with. Is the music out there, or is it only in here? Thank you for joining us on this incredibly detailed journey through the mechanics of reality. We hope you never listen to the world exactly the same way again. Happy learning, and we'll catch you on the next deep dive.